Welcome back. In this module, I want to talk about these ideas of causation and its related idea of counterfactuals, a framework of how we understand causation today. We can go back to this silly rooster experiment I mentioned in one of the earlier modules about the rooster crowing when the sun rises. Nice and correlated, whether it's causal, that's debatable. So statistically speaking, researchers, certainly statisticians, have tried to avoid the word cause for about 100 years, for the most part. There's always exceptions. Statisticians in particular were reluctant to use the word cause outside a randomized trial. Sometimes we call these today randomized clinical trial or randomized controlled trials. Today, that's no longer true. I think it's fair to say there's been a revolution in the social sciences, in the health sciences, and even statistics, that we now freely and, though with difficulty, understand what it takes to say X caused Y. This kind of structural racism, this income inequality causes these health disparities. We want to go back to our story of the sour grapes and, in my view, embrace the challenge of understanding cause and effect. And of course, there's all these words. Association. I'm not quite sure what that means. I think it means correlation, but it seems to imply more than correlation. Little sketchy for me as an epidemiologist. Then correlation, which we'll talk about shortly, and then this idea of causation. How about a little history? Well, from my read, the key player here in this idea of statisticians staying away from causation is the great Karl Pearson. Karl Pearson was a tremendously influential scholar in Britain. He was a social Darwinist, a student of the great mathematician Galton, and he invented the correlation coefficient in 1896. Some of you may recognize the term Pearson correlation coefficient. That's from old Karl himself. Maybe it's worth noting out that Karl is spelled with a K. He changed that himself in order to be more similar to Karl Marx, ironically. Pearson also worked on these things called contingency tables and other kinds of statistical things. Importantly, Pearson rejected the idea of causality. He thought correlation was more important than causation. So today you might hear in a news story, correlation is not causation. That's true. For Pearson, that was more important to be correlated because causal language had no play. By contrast, the other great, if you will, founding father of modern statistical scientific work is Sir Ronald Fisher. Fisher, interestingly, was trying to solve a real-world problem. Fisher was asked by the British government to figure out how to grow more food for troops in the war. So he had a very real problem to solve, much like the problems you and I are trying to solve with respect to health and health disparities. Fisher's challenge was how to figure out, to be simple, how to grow more wheat. What amount of fertilizer? What kind of fertilizer? How much water? How much sun? All of these things are very challenging. So Fisher is trying to figure out what remedy, what intervention he can apply to some crops to get more food for the war effort. I very much like the applied work of Fisher in this way. He, of course, did some great background math, but this applied work was really focused on doing things and being active, and of course, entailing this idea of causation. The other big player in our world is Austin Bradford Hill. Now, Hill sort of took Fisher's ideas and applied it to research for health. He pioneered the randomized clinical trial. And it's this randomized clinical trial, sometimes called RCT, that we can use as a backdrop for understanding whether our interventions on a person or a community improve their health. It's not that we have to do that kind of rigorous experiment, but if we have it as a framework, we can understand our own work better. Critically, and for you statistical people, this will be old stuff. If you don't understand this, that's okay. But Pearson was trying to understand correlations. Fisher and Hill were trying to understand, does this treatment work? For Fisher, are there more crops? For Hill, is health improved? I think it's the latter two that are more akin to the type of work you and I are doing. So that's why I keep pushing on this idea of causal effects. We're trying to do something, we're trying to improve health, trying to mitigate health disparities. What works and what doesn't? Correlations can be a very interesting but dangerous idea. Here's a couple silly correlations that I pulled, of course, from the interwebs. Here you might be able to see a couple of lines over time, where for me the left-hand side of the graphic is 1999 and the right hand is 2009. You see a red and a black line. These lines tend to move together. You'd think that these two things have to be causally related because they move together. When one goes up, the other goes up. When one goes down, the other goes down. Incredibly, these two lines are quite different. The red is just graphing the number of people who drowned by falling into a pool. Horrible, but an interesting statistic. The black is the number of films the actor Nicolas Cage appeared in over time. So we have a correlation between drowning in a pool and the number of films of Nicolas Cage. I just can't believe those are causal, but nevertheless, they're correlated in this strangely unique way. Here's another. Here we have over time, again, a red and a black line. This is per capita consumption of mozzarella cheese, delicious stuff, correlated with the number of civil engineering doctorates awarded. When the consumption of mozzarella cheese goes up, so does civil engineering doctorates. Crazy, but true, correlated, kind of a stretch to be causal. Finally, again, red here, letters in the winning word of the Scripps National Spelling Bee. So letters in the word goes up and down over time. The black line here is the number of people killed by venomous spiders. Horrific. But these two things are correlated, clearly, I think, not causal. This is all to say that we need to be suspicious of correlations and do the extra intellectual work to say X caused Y. This intervention has improved health or not. One way to think about this, there are several ways, but one way is to use this idea or set of ideas we call counterfactuals. Counterfactuals, something that's counter to fact. It's a thought experiment, a mind game, if you will. The idea comes again from the great David Hume in the 1700s, where he was working on induction and talked about but-for assumptions. But for the finger in your side, you wouldn't be laughing. But for the nutritious food, you wouldn't be healthy. But for. This idea then sort of languished for a couple of hundred years, was picked up again by a philosopher and published in a book in 1973. It's a very technical book that I can't get through, but the first line of this book has always struck me. David Lewis wrote, "If kangaroos had no tails, they would topple over." That is, kangaroos don't topple over but for their tails. And he's trying to then go into a very rigorous, mathematically rigorous idea of counterfactuals. The statistician from Harvard, Don Rubin, put this idea into modern statistical frameworks, and today we work on these same ideas all the time. This whole area of comparative effectiveness research that we see in medicine. Pill A or pill B or pill C, what works better, what's least expensive, these kinds of questions. Other things of policy A or policy B, which works better. This is all coming from the counterfactual framework. I want to try to make this as simple as possible, so I'm going to tell you a story with some cartoons that I sort of made up in this PowerPoint presentation. We can just imagine what we'd like to do is to compare two people under the exact same scenario. In other words, it's really one person twice. One person goes through history, and then if we will, we can turn back the clock, change one thing, and run history again. And then we'd see the impact of that change on, say, their life outcome. That's the goal. It's not possible. This is just a thought experiment, but it can illuminate some of the things we need to understand. So in this little PowerPoint presentation, we're going to have two people, two stick people. I label them Ivan, and we see what happens with Ivan's BMI or body mass index when he is exposed to a McDonald's or not. So let's just play through this. Okay, here's Ivan, lovely stick person. And he gets exposed to some McDonald's, and of course, he's loving it. And then what we see over time is Ivan also not exposed. This is the counterfactual. One of these is true. Either he had McDonald's or he didn't. They can't both be true. Ivan either did have McDonald's or didn't. So what happens here? In one case, he's loving it, and you can see he gets a little bit thicker. In the other scenario, he does not have McDonald's, and he stays trim. What matters here is we can precisely calculate the effect of McDonald's consumption on Ivan's body mass index. We can know this because we have Ivan in two separate worlds. In one world with McDonald's, and another world without. It's the exact same person. Everything else in the worlds are the same. One's McDonald's, one's not. Of course, this can't happen in real life. That's why we call it counterfactual. Only one of these happens. But this is how we could say calculate that the change in BMI due to McDonald's on Ivan might be, 20 BMI units or something. This is a thought experiment we use. It's so simple. One person with one scenario, the very same person with a different scenario. That's the ideal, but that can't happen. So what really happens is usually we observe someone who might be, in this case, a little bit bigger BMI compared to someone with a thinner BMI, and we see a difference. But in the real world, we don't get to roll back the clock. So we have Ivan, and let me switch my language now. We have black stick figure to blue stick figure. And the question is, the black stick figure is exposed to McDonald's, and the blue stick figure is not. And we see the black stick figure gets a little thick. And, of course, the blue stick figure does not. So now we have a challenge. Is the difference in BMI due to McDonald's consumption itself? Maybe, but it could also be because the blue stick figure is exercising a lot more, or has some genetic high metabolism, or any other number of explanations. And the reason these other explanations come in is because we didn't get the counterfactual. We have black stick figure and blue stick figure. And if they're not identical in every way, but for the McDonald's, then we have alternative explanations. And this is the key of scientific inference. Did McDonald's cause a change in BMI? Maybe. If we can experiment, as Fisher did, we have a pretty good understanding of that. If we can't experiment, then we have a challenge of understanding whether McDonald's was actually the cause or there was something else causing it, metabolism, air pollution, whatever it might be. This is the great challenge of scientific inference. And we can only, therefore, assess the key assumption of whether the black stick figure and the blue stick figure are identical in every way, but for the McDonald's. That's one of the key assumptions. And we'll talk more about that in the next module.